The heart of our Milky Way should be the most violent, chaotic place in the galaxy. A place where the sheer density of stars and radiation makes it almost impossible for new stars to form. At least, that was the theory. For decades, we thought we had the basic rules of this turbulent cosmic downtown figured out. A region 26,000 light-years away, forever hidden from our eyes by impenetrable veils of gas and dust. Our telescopes could only guess at the secrets locked inside. But when the James Webb Space Telescope pointed its golden eye at this supposedly hostile region, it didn't find a stellar desert. It found something that has sent a wave of genuine surprise through the scientific community, something that challenges our deepest expectations. What Webb has uncovered in the fiery heart of our galaxy, and in the faint ghosts of galaxies, like our own, in the distant past, isn't just a new picture. It's a direct challenge to some of our key assumptions about how stars are born and how galaxies like ours came to be. These discoveries are so profound, so unexpected, that they're prompting a fascinating reevaluation of what we thought we knew. Our elegant models are being stretched and refined, and what's emerging is a universe that's far stranger, more chaotic, and more creative than we ever imagined. To get the scale of this surprise, you first have to appreciate the problem. For as long as we've had telescopes, the center of the Milky Way has been a source of immense frustration. It's right there, in the constellation of Sagittarius, a sprawling metropolis of stars so dense that if you were on a planet there, the night sky would blaze with the light of 1,000,000 suns. But we can't see it, not in visible light anyway. Between us and the galactic core lies a thick cosmic fog, vast dark clouds of interstellar dust, trillions of miles wide, that block our view like an impenetrable wall. For generations of astronomers, it was like trying to study a bustling city from the outskirts through a perpetual dense fog. We knew the basics. We knew it hosted a supermassive black hole, Sagittarius A star, a quiet giant 4 million times the mass of our Sun. And we knew about the Central Molecular Zone, or CMZ, a huge reservoir of dense gas and dust stretching across hundreds of light years, the raw material for new stars. And right there was the first great mystery, a paradox that puzzled scientists for decades. The CMZ is packed with gas, more than enough to fuel a stellar baby boom of epic proportions. By all conventional logic, this region should be furiously churning out new stars. And yet, it wasn't. Observations from older radio and infrared telescopes showed that the star formation rate in the CMZ was bizarrely low, suppressed by a factor of 10 or more, compared to what the sheer amount of gas would suggest. Why? The scientific community buzzed with theories. Maybe the intense gravity was shearing gas clouds apart before they could collapse. Perhaps the turbulence was just too high, a cosmic storm ripping stellar seeds to shreds. Or maybe, as some suspected, invisible forces were putting the brakes on cosmic creation. The debate was active, with plenty of proposed ideas, but no definitive answer. The problem was the fog. We just didn't have the technology to pierce it with enough clarity to see what was really going on. We needed a new kind of eye. And then came Webb, launched and parked 1,000,000 miles from Earth. The James Webb Space Telescope isn't just another telescope. It's a time machine and a ghost seer. Its giant, gold-coated mirror is designed to capture infrared light, the long wavelengths of light that can sail straight through the thick dust clouds that blind other observatories. For the first time, we had an instrument that could peel back the cosmic veil and stare directly into the hidden furnace of the galaxy. Scientists pointed it toward the heart of the Milky Way, expecting to finally get data that would help them solve the mystery of suppressed star formation. They thought they'd find a region governed by complex but understandable rules. They were in for a surprise. The first truly stunning images came from a region near the galactic center known as Sagittarius B2. SGR B2 is a giant molecular cloud, a dense, dark clump of gas and dust that astronomers have long known was a site of star formation. But what Webb revealed was something no model had fully prepared them for. Peering through the dust with its near-infrared camera, NIRCam, Webb uncovered a scene of breathtaking chaos and intensity. Instead of a sluggish, suppressed environment, Webb saw a stellar factory running in what looked like absolute overdrive. The images revealed a dense cluster of massive, brilliant, and incredibly young stars, burning with furious energy. These aren't stars like our sun. These are monsters, dozens of times more massive, blazing with a light that is sculpting and energizing the entire region. Webb's mid-infrared instrument, MIRI, added another layer to the picture, showing the glowing, heated dust cocoons that cradle these stellar infants, revealing the intricate structures of their nurseries. But it was the numbers that really made astronomers take notice. They could now start to calculate the sheer output of this one cloud. Based on Webb's new, incredibly detailed census of young stars, they could refine earlier estimates with stunning precision. It turns out that this single region, Sagittarius B2, is disproportionately productive. While the broader central molecular zone seems to be underperforming, SGR B2 is an extreme overachiever. Some studies now suggest it might be responsible for a remarkably high percentage of all the new stars being born in the entire galactic center, despite containing only a small fraction of the total available gas. Think about that. It's like finding a vast, fertile plain where almost nothing grows, except for one small patch that is erupting with a forest of giant redwoods. It doesn't quite add up. Why is this one cloud so phenomenally efficient at making stars, while its neighbors, filled with the same raw materials, are mostly quiet? Webb's images only deepened the puzzle. They showed that the star birth in SGR B2 isn't a smooth, uniform process. The cloud is a tangled mess of complex filaments, glowing clumps, and turbulent cavities being blown out by the ferocious radiation from the newborn massive stars. It's structured and chaotic at the same time. These new, high-resolution views provided a wealth of data, but instead of solving the old mystery of the CMZ's suppressed star formation, they've replaced it with a new, more urgent one. What makes Sagittarius B2 so special? And what powerful force is holding the rest of the galactic center back? The answer, it seems, may lie in something invisible, powerful, and utterly fascinating. As astronomers pored over Webb's data, another set of images from a nearby region called Sagittarius C provided a critical and fascinating clue. Here, Webb's infrared eyes captured something that had only been hinted at before: vast, eerie, glowing filaments of hot gas stretching for light years through space. These structures, which some astronomers have likened to spaghetti-like noodles, were a serendipitous discovery, and they hinted at a powerful force at play. What could create such organized, large-scale structures in such a chaotic environment? The leading hypothesis is as powerful as it is invisible: magnetic fields. For a while now, scientists using radio observatories have suspected that the entire central molecular zone is threaded with incredibly strong magnetic fields, far more potent than those in the calmer suburbs of the galaxy where we live. These fields are thought to be stretched and twisted by the motion of gas swirling around the supermassive black hole, Sagittarius A star, forming a powerful, invisible web. This magnetic web, scientists propose, may be the very force suppressing star formation across most of the galactic center. Gravity tries to pull clouds of gas together to form new stars, but the magnetic fields can fight back. They can act like a supportive scaffolding, preventing the clouds from collapsing under their own weight. It's a cosmic tug-of-war, and in most of the CMZ, the magnetic fields might be winning. The gas is there, but it could be trapped, unable to form stars. The stunning filaments seen by Webb in Sagittarius C are thought to be visual evidence of this process. They are hot plasma tracing the powerful lines of magnetic force. So why then, Is Sagittarius B2 churning out stars? The tantalizing implication is that SGR B2 must be a place where the conditions are just right to overcome this magnetic braking. Perhaps the cloud is just so massive that its own gravity is overwhelming the magnetic resistance. Or maybe collisions with other clouds have disrupted the magnetic fields locally, triggering a runaway collapse. This isn't just a local puzzle, it has big implications for our understanding of the universe's history. The extreme conditions in the galactic center are thought to be a local analog for the hyper-intense star-forming environments that existed in the very early universe. By studying SGR B2, Webb is giving us a laboratory in our own backyard to witness the kind of extreme star birth that built the first galaxies. The alarming discovery is that our models for how that process works, even here at home, are clearly incomplete. The rules we thought we knew are being challenged, and the invisible hand of magnetism appears to be a far more important character in this cosmic story than we ever gave it credit for. While one part of Webb's gaze was fixed on the birth of stars, another was aimed at the ultimate source of power in the galactic center, the supermassive black hole, Sagittarius A star. For the most part, SGR A star is a sleeping giant. Compared to the ravenous quasars that blaze at the centers of other galaxies, ours is pretty quiet. But it's not completely dormant. It regularly flickers, producing flares of radiation that can be seen across the electromagnetic spectrum. For years, astronomers have observed these flares, trying to piece together the physics of what happens at the very edge of a black hole. But there was a missing piece to the puzzle: the mid-infrared. This part of the spectrum is crucial, but it's impossible to observe from the ground because Earth's atmosphere blocks it. Once again, Webb's location in space gave it a unique advantage. Using its mid-infrared instrument, MIRI, a team of scientists pointed Webb at SGR A star and captured a flare in unprecedented mid-infrared detail. The observation was a breakthrough. The flare provided rich data that allowed scientists to watch how its light changed over its short lifespan. What they found gave powerful new support for a process called synchrotron cooling. This happens when high-energy electrons, sped up to near the speed of light, spiral around intense magnetic field lines and lose energy by emitting radiation. The specific way the mid-infrared light dimmed over time was a telltale signature of this process. This might sound technical, but the implication is pretty cool. It strongly ties the flares of our own, relatively peaceful black hole to the same fundamental physics that powers the most violent objects in the universe, like the jets of active galaxies and quasars. It suggests that the area around SGR A star is a dynamic and magnetically charged environment where particles are being whipped into a frenzy. This discovery doesn't exist in a vacuum. It arrives alongside other recent findings from telescopes like Chandra, which suggest that Sagittarius A star was way more active in the not-so-distant past. Echoes of powerful X-ray flares from hundreds or even thousands of years ago can still be seen lighting up gas clouds far from the black hole. The picture is shifting from a dormant giant to an intermittently active engine. Our galactic center isn't just quiet, it's waiting. Webb's observation of the flare's magnetic nature adds another layer to this. It shows that the mechanisms for much greater violence are present and active, raising fascinating questions about our galaxy's core and what might happen if the sleeping giant ever truly awakens. The James Webb Space Telescope can do more than just peer into the heart of our present-day galaxy. By looking deep into space, it looks back in time, acting as a cosmic historian. It can't see our own Milky Way's past, but it can do the next best thing. It can find and study galaxies that are analogs of our own from much earlier in cosmic history. And what it's finding about our galaxy's childhood is profoundly unsettling for our neat models of quiet, orderly growth. For a long time, a popular picture of galaxy formation involved a relatively smooth process. A giant halo of dark matter would slowly pull in gas, which would settle into a calm, rotating disk, and that disk would gracefully form stars over billions of years. But Webb's observations of Milky Way twins are painting a far more brutal and chaotic picture of our origins. A recent study combined data from both Webb and Hubble to trace the history of galaxies like our own, back to a time when the universe was just a few billion years old. The findings support a pattern of inside-out growth. The dense central bulges of these galaxies formed first, and the outer spiral disks were built up later. But the process was anything but gentle. The images from Webb reveal that these young Milky Way progenitors were not the serene, majestic spirals we see today. They were messy, clumpy, and disturbed systems. Their shapes were asymmetric and irregular, clear evidence that they were undergoing frequent and violent collisions with other galaxies. Instead of forming stars at a steady rate, they were experiencing intense, powerful bursts of star formation, likely triggered by these cosmic pileups. The gas within these galaxies wasn't settling into neat orbits. Instead, Webb's instruments show it was a turbulent, chaotic mess, with gas moving in all directions at once. These galaxies were puffed up, unstable, and anything but settled. This violent youth is prompting scientists to refine their understanding of how a galaxy like ours could have even survived. If our past was so tumultuous, how did the beautiful, thin, fragile spiral disk of the Milky Way emerge and remain so well-ordered? The discovery that our galaxy's history was far messier than some models assumed isn't just a historical footnote. It creates a genuine tension in our theories, forcing us to ask new questions about the resilience of galactic structures and the powerful forces that eventually tamed the chaos to create the magnificent galactic home we know today. The story gets even stranger. If uncovering the Milky Way's violent past was unsettling, what Webb found in the even deeper universe was, for some, genuinely puzzling. As Webb peered back to the cosmic dawn, to a time just 1.5 billion years after the Big Bang, it spotted something that, according to many existing models, was a bit of a surprise. Researchers found candidates for massive, well-ordered galaxies that seemed remarkably mature for their age. One such galaxy, for example, appears to be a cosmic giant for its time, already containing the mass of billions of stars and showing signs of a distinct central bulge and even prominent spiral arms. Here's the problem. It all seems a bit too perfect, a bit too early. The classic theory of galaxy formation predicted that the early universe should be filled with chaotic, irregular, and clumpy galaxies, the kind of messy systems Webb saw in the Milky Way's teenage years. The formation of a stable, rotating disk with elegant spiral arms was thought to be a slow, delicate process that would take many billions of years. It required the gas in a galaxy to cool down, settle, and remain largely undisturbed by the constant, violent mergers that characterized the early cosmos. The existence of such advanced-looking galaxies so early on throws a wrench in that timeline. It suggests that the process of galaxy maturation can happen far more rapidly and efficiently than our models accounted for. To assemble that much mass and organize it into a structured disk in such a short amount of time, when the universe was barely a tenth of its current age, challenges our fundamental understanding of galaxy assembly. It means that either gas can cool and settle into disks much faster, or that spiral patterns can be generated more quickly than we believed. This isn't just a pretty picture, it's a profound temporal puzzle. It's a bit like finding a fully grown ancient oak tree that is only a few years old. The discovery is so significant because it adds to a growing body of evidence from Webb that the early universe was far more mature and capable of building complex structures than we ever imagined. The existence of such candidates is forcing astronomers to go back to the drawing board. They're now faced with an exciting new reality. The universe was in a hurry, and our theories haven't yet caught up with its astonishing speed. Beyond finding galaxies that were too mature, Webb also started finding galaxies that were just weird. In the treasure trove of data from surveys like the Cosmic Evolution Early Release Science Survey, or SEERS, astronomers identified a population of bizarre objects they nicknamed platypus galaxies. Like the animal, which combines features of mammals, birds, and reptiles, these galaxies mix and match characteristics that shouldn't really exist together. From a distance, they look like tiny, compact point sources, almost like stars or distant quasars. But when Webb analyzed the light coming from them, it found something else entirely. Their light signatures didn't have the telltale signs of a supermassive black hole devouring matter, which is what you'd expect from a quasar. Instead, they showed the sharp emission lines characteristic of active star formation, something you see in a larger galaxy. So they look like quasars, but act like galaxies. This perplexing combination resists our neat classification schemes and suggests we may be seeing an entirely new class of object for the first time. But perhaps the most profound puzzle of all touches on the invisible scaffolding of the universe: dark matter. The standard model of cosmology is built on cold dark matter, a type of slow-moving particle that clumps together, forming the seeds around which all galaxies grow. This model has been incredibly successful at explaining the large-scale structure of the universe. However, it's had some tensions when trying to explain structures on smaller, galactic scales. Now, Webb has provided an intriguing new observation that is adding to this tension. In the very early universe, Webb has found a number of young galaxies that are unexpectedly elongated, with prolate or cigar-like shapes. They look more like smooth cosmic filaments than the rounder, clumpier shapes you might expect. New, cutting-edge simulations have started to compare this observation with different theories of dark matter. When they simulate a universe with standard cold dark matter, they sometimes struggle to produce so many of these highly elongated galaxies. But when they run simulations with alternative models, like warm dark matter or even more exotic fuzzy dark matter, they find something remarkable. These models can more easily produce smoother cosmic filaments in the early universe, which in turn could naturally form the exact kind of elongated galaxies that Webb is observing. Now, this is not proof that cold dark matter is wrong, but it is one of the most interesting observational clues we've had in a while that the nature of dark matter might be more complex than our simplest models suggest. It has opened a new and exciting line of inquiry, raising the possibility that we might need to revise our understanding of the universe's invisible matter. That's a question with consequences that ripple through all of cosmology, all thanks to the unexpected shapes of the first galaxies seen by Webb. So what does all of this mean when you put it together? From the hyper-efficient star factory of Sagittarius B2 in our own galactic backyard, to the flickering magnetic heart of Sagittarius A star, to the messy childhood of our own Milky Way, to the impossible maturity of the universe's first galaxies, a single, consistent, and fascinating theme is emerging. The universe appears to be more complex, evolves faster, and behaves in more unexpected ways than our established models predicted. For decades, cosmology and astrophysics have been built on a framework of gradual, orderly evolution governed by gravity. But Webb's observations are consistently revealing a cosmos where processes are accelerated, where structures appear too early, and where other forces, like magnetism, seem to play a far more critical role than we appreciated. The alarm rippling through the scientific community isn't one of crisis. It's the thrill of discovery mixed with the humbling realization that our picture was incomplete. When a single star factory defies the rules of its environment, it's a puzzle. When our own supermassive black hole shows hints of the same physics as a violent quasar, it's a new chapter. When our galaxy's entire history is revealed to be more brutal than we thought, it forces a revision. And when the very shapes of the first galaxies hint that we might not fully understand the nature of dark matter, it becomes a profound opportunity for new science. This is not a sign that our science is broken. It is a sign that it is working. The James Webb Space Telescope was built to push the boundaries of our knowledge, and it is doing exactly that. It is challenging assumptions, forcing scientists to refine their models, and opening up entirely new fields of inquiry. We are being forced to account for a universe that is more creative, more dynamic, and far stranger than we ever knew. We are not just getting new answers. We are finding that we didn't even know all the right questions to ask. So, what has the James Webb Space Telescope truly shown us by peering deeper into the Milky Way and its cosmic ancestors? It has shown us a star-forming region in our own galaxy's heart that operates with an efficiency that defies our simple explanations. It has revealed our central black hole to be a magnetically charged engine, flickering with the same fire that powers the most luminous objects in the cosmos. It has painted a new history of our own galaxy, one forged in chaos and violence. And in the echoes of the Big Bang, it has found galaxies that matured too quickly and whose very shapes may be whispering a new secret about the nature of dark matter itself. Each of these discoveries on its own would be the subject of scientific debate for years, but taken together, they represent a fundamental shift. We are moving away from a picture of slow, stately cosmic evolution and toward one of rapid, turbulent, and magnetically sculpted creation. The elegant models of the past are not being thrown out, but they are being stretched, amended, and challenged in ways that would have been unimaginable just a few years ago. This is just the beginning. Webb will continue to stare into the cosmic dark, and with every new image, it will either help solve these profound new mysteries, or, just as likely, deepen them. We are living in a golden age of astronomy, a moment where the story of the universe is being actively rewritten, right before our eyes. The surprise is real, but it is the exhilarating surprise of explorers who have just crested a hill and realized the map they were holding no longer describes the vast, new, and unknown territory that lies before them. The James Webb Space Telescope has not just opened a window to the universe, it has shattered our assumptions and invited us to completely reimagine the cosmic story. And that journey of discovery has only just begun.